Principal component analysis (PCA) is behind facial recognition, data compression, and more. This video shows you exactly how its core idea works, line by line using Python. PCA or principal component analysis is a powerful technique for reducing the dimensionality of data while preserving what matters most. Why should we care? Here's why. It helps us visualize high dimensional data by projecting it into 2 or 3 dimensions. By that, it removes redundant features, keeping only most relevant ones. It speeds up machine learning models and reduce overfitting. And most importantly, it makes complex data easier to interpret. In this video, we are going to walk through a Python script that performs PCA from scratch using just NumPy. No libraries doing heavy lifting for us. We will do the math by ourselves. We will begin by importing NumPy. It's the core library we will use for matrix operation and linear algebra. Here's our data set. 2 dimensions of 8 values. Think of each row as a variable and each column as a data point. So we have 8 observations of 2 variables. The goal of the PCA is to reduce this 2D data into new axis, one that captures the most variation in the data and projects our data onto that axis. In step 1, we center the data. Why? Because PCA is all about the variation, not the absolute values. We subtract the mean of each row, so both variables are centered around 0. Let's break it down. This np.mean calculates the mean of each row, giving us a 2 by 1 column vector. And this x-centered subtracts that mean from every value in the corresponding row. Can see this x-centered. Each value is subtracted by its corresponding mean value. The result is x-centered, which is our mean centered data, is now ready for PCA. And you can see this graph is before centering the data and this graph is after centering the data. You can see all the 8 data points we had. 1, 2, 3, 4, 5, 6, 7, 8. All the data points have been centered. Next, we calculate the covariance matrix. This tells us how much the two variables vary together. If the covariance is high and positive, they move in the same direction. If it is high and negative, they move in opposite directions. If it's close to 0, they are mostly independent. This np.cob gives us a 2 by 2 matrix. The diagonal shows the variance of each variable. Now for the heart of PCA, which is Eigen decomposition, this np.linalg.eig takes the covariance matrix and breaks it into eigenvalues and eigenvectors. Each eigenvalue tells us how much variance is captured in the direction of its corresponding eigenvector. The eigenvectors themselves are directions in space. And think of them as the new axis we are trying to find. These eigenvectors are what PCA uses to define the new rooted coordinated system. And these are our eigenvalues, and we always need to normalize the eigenvectors before using it. You can see here, this is the normalized version of one eigenvalue, and this is for the another eigenvalue. This is the eigenvectors for their corresponding eigenvalues. By default, np.linalg.eag, which we saw in the previous step, gives us the eigenvalues in random order. So here we sort them. np.arg sort, this one gives us the indices that would sort them from largest to smallest. We reorder both eigenvalues and eigenvectors accordingly. We need to sort because the first principal component should capture the most variance we want to project onto the direction with the highest eigenvalue, and the eigenvalue is 19.849 and its corresponding eigenvector is minus 0.543 and minus 0.835. Now we project our data onto the first principal component, the direction that captures the most variation. This PC1 is the first column in the sorted eigenvectors or the first principal component. Y performs a dot product to project each point from two-dimensional data onto this new one-dimensional axis. The result Y is the one-dimensional representation of our original two-dimensional data. This is dimensionality reduction or PCA. This step is very easy, that we just need to multiply the W transpose, which is the first principal component, by the X centered value we found in the first step. And you can see that this is the one-dimensional representation of our two-dimensional data. Now that we have projected our data into one dimension, it's time to bring it back or reconstruct it to its original space. This line of code matches exactly what's shown in the formula. As you can see that the reconstructed data is almost close to the real data. The result X reconstructed an approximation of the original data set reconstructed from just one principal component. Finally, we printed the reconstructed data. If everything went well, this data should look very close to the original data. Not exact, but pretty close. Here's a challenge for you. Try adding a second principal component to the reconstruction and see how the result improve Use your own dataset, apply PCA step by step, and reconstruct it yourself. That's the best way to make this stick. And that's it. You have just walked through principal component analysis from the ground up using pure Python and NumPy. If you made it this far seriously, well then, you didn't just run code, you understood the math behind one of the most powerful tool in machine learning. Whether you are working on data compression, visualization, or just leveling up your skills, understanding PCA is a huge step. Take a moment to try it yourself. Change the data. Add another principal component. Break it, fix it. That's where your real learning happens. Thanks for spending this time with me, and I will see you in the next one.